Somewhere out in space, right now, there's a monster so powerful that even light, the fastest thing in the entire universe, cannot escape it. Not lasers. Not sunlight. Not even the light from your phone screen. Nothing. It doesn't explode. It doesn't roar. It just waits, silently bending space and time around it like a black curtain being pulled over the universe. Scientists call it a black hole. And by the end of this video, you'll understand exactly how something that eats light can exist and why one might be closer than you think. Stick around because minute 19 is going to blow your mind. Let's start at the very beginning, with a star and its slow, secret countdown to death. Before we talk about black holes, we need to talk about stars because every black hole used to be one. A star, like our sun, is basically a giant ball of gas locked in a tug-of-war. On one side, gravity, constantly trying to crush the star inward. On the other side, nuclear fusion, an explosion of energy from hydrogen atoms slamming together in the core, pushing outward. As long as those two forces are balanced, the star just shines. Peacefully. For billions of years. Our sun has been doing this exact balancing act for 4.6 billion years, and it's got about 5 billion more to go. But not every star gets that lucky. Some stars are born bigger, angrier, and hungrier, and that changes everything. Let's quickly understand gravity, because it's the villain, or maybe the hero, of this whole story. Gravity is simply the pull that any object with mass has on any other object with mass. The more mass, the stronger the pull. Earth pulls you down. The sun pulls Earth around it. And a star pulls its own gas inward, always. Imagine gravity as an invisible hand constantly squeezing a stress ball. As long as something pushes back, like fusion does inside a star, the ball holds its shape. But take away that pushback, even for a moment, and the invisible hand wins instantly. This is exactly what happens at the end of a massive star's life. The pushback disappears. And gravity finally gets what it's always wanted. Picture a star at least 20 times more massive than our sun. For millions of years, it's been fusing hydrogen into helium, helium into carbon, carbon into neon, all the way up the periodic table. Each step releasing a little less energy than the last. It's like a fire slowly running out of fuel to burn. Eventually, the star fuses its way to iron. And here's the cosmic joke. Iron cannot be fused for energy. It takes energy instead of releasing it. The star has officially hit rock bottom. The outward push that held gravity back for millions of years suddenly, catastrophically, stops. In less than 1 second, faster than you can blink, the star's core begins to collapse in on itself. The core collapses in a fraction of a second, and the outer layers of the star come crashing down on top of it, then bounce violently back outward in one of the most powerful explosions in the universe, a supernova. For a few weeks, this single dying star can outshine its entire galaxy, billions of other stars combined. It's so bright that ancient civilizations recorded new stars appearing in daylight skies without knowing what they were really witnessing, a death. A supernova scatters heavy elements, carbon, oxygen, iron, even gold, across space. Fun fact, the calcium in your bones and the iron in your blood were forged inside a star that exploded like this. You are quite literally made of dead stars. While the outer layers of the star are blasting outward in the supernova, something very different is happening at the very center. The core, now only the leftover mass, incredibly dense, keeps collapsing. Gravity has already won here. There's no fusion left to fight back. If the leftover core is somewhere between about 1.4 and 3 times the mass of our sun, it usually collapses into an ultra-dense object called a neutron star, so dense that a teaspoon of it would weigh about 1 billion tons on Earth. But if the leftover core is even heavier than that, more than roughly 3 solar masses, neutron star density isn't enough to stop it. There is nothing left in physics that can resist gravity now. The collapse doesn't stop. It just keeps going. This is the moment. The core keeps shrinking, past the density of a neutron star, past anything we can really picture, collapsing toward an infinitely small point. As it does, its gravity becomes so extreme that it starts warping the space around it, not just pulling on nearby objects, but bending the actual fabric of space and time itself. Once the collapse crosses a certain point, it creates a region where the escape speed, the speed you'd need to break free, becomes faster than the speed of light. And since nothing can travel faster than light, nothing can escape. Not gas, not radiation, not information, not light itself. A black hole isn't really a hole at all. It's a region of space where gravity has simply won completely. Every black hole has an invisible boundary around it called the event horizon. Think of it as the ultimate no refunds line in the universe. Cross it, and there is no coming back, not because of a locked door, but because of the laws of physics themselves. Outside the event horizon, you could still, theoretically, escape if you had a powerful enough engine. The instant you cross it, escape becomes mathematically impossible, no matter how strong your rocket is. Interestingly, the event horizon itself isn't a physical wall. You might not even notice the exact moment you cross it, especially around a giant black hole. It's calm right up until it's absolutely, permanently, not. That's what makes black holes so eerie. The danger is invisible until it's too late. At the very center of a black hole lies something even stranger than the event horizon, the singularity. This is the point where, according to our current equations, all that collapsed matter gets squeezed into zero volume and infinite density. Zero size. Infinite density. Read that again, it sounds impossible because honestly, it kind of is. This is the point where Einstein's theory of general relativity, which describes gravity beautifully everywhere else in the universe, completely breaks down and stops giving useful answers. Many physicists believe the singularity isn't really infinite in reality. It's a sign that we're missing a piece of physics, something that only shows up when gravity gets combined with quantum mechanics. In other words, the center of a black hole is where our best science admits we don't fully know yet. Here's where things get truly mind-bending. Black holes don't just bend space, they bend time. According to Einstein, gravity slows down time itself, and near a black hole, gravity is as extreme as it gets. Picture two friends. One stays in a spaceship far away, the other flies close to the event horizon and hovers there for what feels like 1 hour to them. When they return to their friend, decades might have passed outside. This isn't science fiction, it's called gravitational time dilation, and it's been measured, in much weaker form, right here on Earth using satellites and precise atomic clocks. Near a black hole, the effect is extreme. Time doesn't just fly. Down there, it practically stops. If you got too close to a black hole feet first, physicists have an actual, official term for what would happen to you. Spaghettification.
Here's why.
Gravity gets dramatically stronger the closer you are to something. So, if your feet are closer to the black hole than your head, the pull on your feet becomes way stronger than the pull on your head. Your body gets stretched, longer and thinner like a piece of spaghetti being pulled from both ends. This stretching effect is called tidal forces, the same basic idea that causes ocean tides on Earth, just at an unimaginably extreme level. Around a small black hole, this would happen long before you even reach the event horizon. Around a supermassive one, you might actually cross the horizon in one piece first. Small comfort. Let's run a thought experiment. Say you fall toward a supermassive black hole, big enough that tidal forces near the edge are gentle. From your point of view, falling and feels surprisingly uneventful at first. You wouldn't see a wall or a barrier. You'd just keep falling. But here's the twist. Someone watching you from a safe distance would never actually see you cross the event horizon. Because light takes longer and longer to escape as you get closer, from their perspective you'd appear to slow down, freeze, and fade, forever approaching the edge in extreme slow motion, like a photo that never finishes loading. Two totally different realities, both technically true, depending on where you're standing. This is one of the most brain-melting consequences of relativity. Here's something a lot of people get wrong. Black holes aren't all giant space monsters swallowing entire solar systems. They actually come in different size categories. The smallest confirmed type is the stellar mass black hole, formed the exact way we just described, from a collapsing massive star. These typically weigh somewhere between about 5 and a few dozen times the mass of our Sun. Despite that huge mass, a stellar black hole is surprisingly compact, One with roughly the sun's mass squeezed down would only be a few kilometers across. Our galaxy alone is estimated to contain tens of millions of these stellar mass black holes, quietly drifting through space, mostly invisible, mostly harmless from a safe distance. But stellar mass black holes are just the beginning of the size chart. Now for the real giants, supermassive black holes. These monsters can weigh anywhere from hundreds of thousands to billions of times the mass of our sun. And here's the wild part. Scientists believe nearly every large galaxy in the universe, including our own Milky Way, has one of these giants sitting quietly at its very center. Not eating everything nearby like popular movies suggest, usually just sitting there, orbited by billions of stars, the same way the sun sits at the center of our solar system. Nobody fully knows how supermassive black holes got so big so early in the universe's history. It's one of the biggest open questions in modern astrophysics. But we do know exactly where the nearest one is. It's closer to home than you'd think. At the exact center of our own Milky Way galaxy sits a supermassive black hole called Sagittarius A star, or Sagittarius A** for short. It weighs around 4 million times the mass of our sun. Don't panic. It's about 26,000 light-years away, meaning even light takes 26,000 years to travel from here to there. We are in absolutely no danger from it. In fact, for most of human history, we didn't even know it existed because it doesn't glow or explode. It's quiet, almost dormant, slowly orbited by nearby stars whose strange, fast, curved paths were actually the biggest clue that something invisible and impossibly massive was sitting there. Scientists tracked those orbiting stars for decades before they were confident enough to say, yes, there's a black hole at the heart of our home galaxy. Here's a genuinely strange question. If black holes trap light, how did scientists ever manage to take an actual photo of one? In 2019, a global team called the Event Horizon Telescope Project released the first ever image of a black hole's shadow, located in a distant galaxy called M87. They didn't photograph the black hole itself. Remember, it traps all light. Instead, they photographed the glowing ring of superheated gas and dust swirling just outside the event horizon, silhouetting the dark region in the middle. To pull this off, they linked together radio telescopes from all around the planet, effectively creating a telescope the size of Earth itself. The final image looked like a fiery orange donut wrapped around a perfect black circle, and it instantly became one of the most famous photographs in scientific history. Because black holes bend time so dramatically, some scientists and science fiction writers have wondered, could they be used for time travel? Technically, sort of, but not the way movies show it. Remember gravitational time dilation from earlier? If you orbited safely near a massive black hole's edge for what felt like a few hours to you, decades could pass back on Earth. That means you'd essentially be traveling into Earth's future, a real, physics-approved form of one-way time travel, demonstrated in the movie Interstellar using real relativity equations. But going backward in time, visiting your own past, running into your younger self? That's a completely different, far more speculative idea that would require something like a traversable wormhole, and that brings us to black holes' strange theoretical cousin. Here's something that surprises almost everyone. Black holes might not last forever. In the 1970s, physicist Stephen Hawking proposed that black holes very slowly leak energy over time through a process now called Hawking radiation. The basic idea involves quantum physics near the event horizon, where pairs of particles constantly pop in and out of existence. Occasionally, one particle of a pair falls in while the other escapes, and that escaping particle carries away a tiny bit of the black hole's mass and energy. Over unimaginably long timescales, far longer than the current age of the universe, this process could cause a black hole to slowly shrink and eventually evaporate completely. For massive black holes, we're talking timescales longer than a number followed by dozens of zeros. But in theory, even black holes aren't truly forever. This is the mind-blower I promised you back in minute 1. Einstein's equations technically allow for something called an Einstein-Rosen bridge, more commonly known as a wormhole, a theoretical shortcut connecting two extremely distant points in space and time, kind of like folding a piece of paper and punching a hole through both layers instead of walking across the whole sheet. Some versions of the math even connect black holes to hypothetical white holes on the other end, regions that only spit matter out instead of pulling it in. Here's the catch. Nobody has ever observed a wormhole, and most physicists believe they'd instantly collapse the moment anything tried to pass through, unless held open by an exotic form of matter we've never actually detected. So for now, wormholes remain one of the universe's most fascinating maybes. Let's shut down a common fear right now. No, a black hole is not secretly approaching Earth to swallow us whole. And no, the Large Hadron Collider isn't going to accidentally create one that destroys the planet. That particular myth got debunked years ago by actual physicists. Here's the key thing people misunderstand. Black holes don't have some magical supervacuum power that reaches out and sucks in everything nearby. Their gravity works exactly like any other object's gravity, based on mass and distance. If our sun were somehow replaced with a black hole of the exact same mass tomorrow, Earth's orbit wouldn't change at all. We'd just lose our light and heat, which, admittedly, would be a much bigger problem. The nearest known black hole to Earth is roughly 1,560 light-years away. We are safe. Genuinely, comfortably safe. So, what's actually inside a black hole? Beyond the event horizon? Here's the honest, slightly unsatisfying truth. We don't fully know, and we currently can't know for certain, because no information can ever escape to tell us. Everything we've discussed, the singularity, the extreme physics, comes from mathematical predictions based on general relativity, extended into a zone where relativity and quantum mechanics start to contradict each other. Solving that contradiction is considered one of the biggest unsolved problems in all of physics, sometimes called the search for a theory of quantum gravity. Some scientists have even proposed wild alternative ideas, that the interior isn't a singularity at all, but something stranger, like a fuzzball of vibrating strings, or even a doorway to another region of space-time entirely. Nobody knows for sure yet. And honestly, that mystery is part of what makes black holes so endlessly fascinating. Believe it or not, scientists don't just study black holes out of curiosity. They're incredibly useful cosmic laboratories. Because they represent the most extreme gravity in the universe, black holes let physicists test Einstein's theory of relativity in conditions we could never recreate on Earth. When two black holes collide and merge, an event so violent it ripples the fabric of space itself, we can now actually detect those ripples, called gravitational waves, using incredibly sensitive detectors on Earth. The first such detection happened in 2015, confirming a 100-year-old prediction from Einstein and opening up an entirely new way of listening to the universe, instead of just looking at it. In a sense, black holes accidentally became one of humanity's best tools for understanding the deepest laws of physics. So where does this leave us? Some scientists have even proposed wild, far-future ideas, like using a black hole's Hawking radiation as an almost limitless energy source, or using the extreme time dilation near one as a way to fast-forward astronauts safely into the distant future. These ideas remain firmly in the realm of theoretical physics for now, requiring technology far beyond anything we currently have. But that's exactly the pattern of scientific progress. Ideas that sound like pure science fiction today have a habit of becoming tomorrow's engineering problems. 100 years ago, the very idea of photographing a black hole's shadow would have sounded absurd. Yet in 2019, we did exactly that. Who knows what black holes might teach us, or offer us 100 years from now? Let's quickly recap this cosmic journey. A massive star burns through its fuel and eventually collapses, triggering a supernova explosion. If the leftover core is heavy enough, gravity wins completely, crushing it past the point where even light can escape, creating a black hole. Every black hole has an event horizon, a point of no return, and possibly a singularity at its center, where our current physics runs out of answers. Near a black hole, time slows down dramatically, and objects get stretched through spaghettification. Black holes range from stellar mass to supermassive, with one, Sagittarius A*, sitting quietly at the center of our own galaxy. And thanks to the Event Horizon Telescope, we've even managed to photograph one. Wild, right? The universe hid one of its strangest secrets in plain sight for the entire history of human civilization. Here's the thing that gets me every single time. The same universe that built black holes also built you. The elements in your body, the atoms in your bones, were forged inside dying stars, some of which may have collapsed into exactly the kind of object we just spent 25 minutes exploring. You are made of star stuff that survived long enough to ask questions about the very forces that created it. That's not just cool trivia. That's genuinely one of the most beautiful facts in all of science. If your mind got stretched a little today, pun absolutely intended, smash that subscribe button because next time we're diving into something just as wild. Insert next topic teaser here. Until then, keep looking up.